Okay, so we continue today with the divergence theorem. Remember, to remind you, we started the divergence theorem. So this was the formula converting the surface integral to a triple integral. And that's done only if your surface is closed and when the normal vector is the outward normal vector. We did the sphere example, and remember, we did the same example using the definition, which is using the parameterization. And I think now everybody appreciates the divergence theorem, because when we compare, these are the computations using the parameterization. So we can look at all these computations, while the divergence theorem can do the same computations in a very simple way. So this is the significance of the divergence theorem. Let's see another example. So for example, let's take the function f as, and I think now everybody agrees that the function is not a big deal. After all, it's just a matter of computations. 2 minus x, z, and let us be the surface, let's say x squared plus y squared equals 1, z between 0 and 1. This is union x squared plus y squared less than or equal to 1 when z is equal to 0 and 1. And we want to compute, so the question is, let's find the surface integral f dot n dA, where n is the outward normal vector. The first thing, we need to understand our surface. So what is our surface? X squared plus y squared equals 1. That's a circle in R2, but we're dealing with R3. So that means we're dealing with a cylinder by extending the circle. And this is not an infinite cylinder, because we are given that z is from 0 to 1. So this is the first part of the surface. Then we make a union with x squared plus y squared less than or equal to 1. Now what is this? This is the disk at the 0 level and at the 1 level. So basically, in this example, so S is a closed surface. If it's a closed surface, that means we can apply the divergence theorem. So we have a triple integral over what? Over the solid bounded by this surface for divergence of. Now what is divergence of? We differentiate the first coordinate with respect to x, plus the second coordinate with respect to y, plus the third coordinate with respect to z, and this is our solid. Now the nice thing, if we look at 2xy for this, so this is my solid, x times y, this has all possible values, positive and negative values. So after doing all the computations, this will be 0. So basically what's left is just the triple integral over this solid dv, which is the volume of the cylinder, which is pi r squared times the height, which is pi. So this is how we do it using the divergence theorem. If we want to do the same example using the parameterization, it would take a long way more than this. So this is the easy computations we can perform using the divergence theorem. Now the question is it always this way? No, it depends. So sometimes the triple integral is much harder than the parameterization, but we're doing these examples to convince you of the significance of the divergence theorem.